about something called calorimetry. So what's that sound like?
Calorie.
The calorie, right? And calorimetry is the science of measuring heat. So when we talk about calories and like our food labels and stuff, we're talking about the amount of energy that is involved in when it's turned into heat. Because when you think about it, okay, you eat food, right? What is most of that food doing for you?
Turning into energy.
Yep, but to do what?
Work.
Even more than that. To heat. To keep you warm. Most of your energy goes into keeping you warm. Now, of course, some of the energy goes into building parts of your body and maintaining parts of your body and, you know, running all the chemical reactions and everything. But think about it. You are a warm being and you're radiating heat all the time. So you have to replace that heat, okay? Just as a side note, we're not going to get too deep into this, but the calorie that we talk about in chemistry class is this calorie. The amount of energy it takes to raise that thing by 1 degree Celsius. That's the amount of heat energy. Okay, so it's not a lot of energy, but it's measurable. The amount of energy it takes to heat this is the calorie that they're talking on your food label. So for whatever reason, people think that Americans are dumb or something like that. Even though that this thing on the food label is called a kilocalorie, we seem to want to call it a calorie, but it's actually a kilocalorie. In fact, if you go and you buy something from Europe or you buy something from South America or something like that on a food label, it'll say kcal on the label. It won't say cal. Right? Now, as a note, when we have calorie on our label, it's a capital C. And that's an indication that it's a kilocalorie. So not to be confusing, but that's just a point to be made. Okay, now, the way we measure heat, one way we can measure heat is in something called the calorimeter. So just like a thermometer measures temperature and a barometer measures air pressure, a calorimeter, well, that measures calories. It's pretty neat when they make these calorimeters. Well, first let's just say it's a device. A device used to measure the heat of a chemical reaction. Calorimeters. So like what a calorimeter is kind of like is imagine a device that's kind of like a cooler first of all. Okay, so you can put something in the cooler and confine it to that space, and it's insulated so any heat that you generate doesn't leak out into the outside world too easily. Okay, now in a cooler, do you know inside the walls of a cooler there's usually like some kind of insulation or just air? Okay, like if you were to slice a cooler open, there would be a hollow space or something filled with like foam or something. Well, in the calorimeter, it's filled with water. Okay, so when a chemical reaction takes place inside this cooler, it heats up the inside of the container, which then in turn heats up the water that surrounds it. Follow me? So what we do is we monitor the temperature of the water, and we know how much water responds to heat. So what we can do when we make one of these machines, and this is what they do actually for each machine, is when it comes off the assembly line, they test it and they see how exactly that particular device responds to heat. So one comes off the assembly line and it might be 5 kilojoules raises the temperature 1 degree Celsius. But maybe the next one that comes off the assembly line is 5.01 kilojoules, raise it 1 degree Celsius. You follow me? There's variations from machine to machine. And so generally on these machines, what they do is they have a little badge on them, and it's stamped, and it says, this is how this machine responds to heat, this particular device. And we call that heat capacity. Heat capacity. And that is usually designated by the letter C. Okay, and this is C equals heat absorbed divided by an increase in temp. So again, that would be some kind of so many joules per so many degrees Celsius. So we'll do some examples of that later on. So what this does is this describes a calorimeter's temperature response to heat. So like what you can do is a lot of times what they use something called a bomb calorimeter. And it's just like it sounds. It's like they ignite something. And so let's say you wanted to find out how many calories were in a candy bar. Well, you take a candy bar, you put it in the bomb calorimeter, and you ignite it. And you burn it up until it's completely burned up. And all the heat that came out of that then gets measured. And obviously in a candy bar, there's going to be a decent amount of calories. There's a lot of fats in there and things that'll burn pretty good. Okay, so heat, this is where we got to be careful because terms are alike. Heat capacity is describing a machine's response to heat. Particular device, okay? Specific heat capacity is something different. Specific heat capacity, we're going to use the letter S. Sometimes we use different letters and different things. This describes a substance's temperature response to heat. Oops. A substance's temperature response to heat. So you guys probably know that, the reason we use metal pans on our stove is because they heat up very quickly. Their temperature rises fast. But there are other things where temperature does not change so quickly, and we call those things insulators. So we might put fiberglass in your house to insulate, to make the temperature change not so abrupt. So specific heat is S equals Q over M delta T. S equals Q over M delta T, where this is specific heat capacity, or I'm just going to call it specific heat. What's Q? Now? Heat. Anybody want to take a wild guess at what M is? Mass. And delta T is? Change in temperature. Okay, so units then would be specific heat would be joules this time, not joules or kilojoules, joules. Mass would be in grams. Temperature change would be in Kelvin or degrees C. So that means specific heat has some crazy units, okay? It is joules per gram times degrees C. Now I could say degrees Kelvin too, but I'm just going to write degrees C for now. Could be Kelvin. Okay, now.
That's grams times degrees C, you said?
Yep, times degrees C. So C, yep.
How do you determine whether they use joules or kilojoules again?
Well, in the other equations, it didn't matter. If it could be joules or kilojoules.
Oh, so this one is just...
This one, it has to be in joules, yep. Okay, so let me make sure I get the right side of the paper. On this side. Bottom left. Okay, so C, back of the periodic table. So if you look at the back of the periodic table, so for example, let's say we have zinc. Okay, so I'm gonna draw what it looks like on the back of the periodic table. They have zinc. They have this hexagon thing here. And then they got a little split here. And down here on the bottom, there's a number that says 0.3386. Man, my eyes aren't that good. God, is that hard to see. 388. 388. This right here is specific heat. See, this is a specific heat of zinc. And that's equal to 0.388 joules per gram times degrees Celsius. So what that's saying is it takes that many joules to raise 1 gram of zinc by 1 degree Celsius. Okay? And so when you look at things like metals are going to have very low numbers. Insulators are going to have really high numbers. Really low numbers are like that. That's a relatively low number for specific heat. A really high number would be like for water. Water is 4.184. So it's something like on the order of 12 times bigger, you know. So it takes 12 times more energy to heat up water than it does this metal.
What is degrees?
Degrees C. It's a temperature. So it says it takes that much energy to raise 1 gram by 1 degree Celsius. Does that make sense?
Yeah.
And I just want to make sure that that's just the number. Okay. All right. So let's see. Another conversion factor you might need. Is 4.184 joules is equal to 1. So again, we're talking the chemistry calorie. So again, if I have, this actually is the amount of energy that it takes to raise that by 1 degree Celsius. That's a calorie, the kind we're talking in chemistry, right? Again, on your food label, it'd be 1,000 times bigger. Right, so you might need to be able to convert between joules and calories. Back and forth. Okay. Another thing we could talk about would be molar heat capacity. So we have heat capacity, which describes a machine. We have specific heat capacity that talks how a substance responds to heat in terms of grams. This is going to be in terms of moles. So this would be, let me do it. This is going to be joules per mole times degrees C.
What's the symbol for that?
Molar heat capacity, I don't think I really have one for you for that. And I don't know why I don't, but I don't. Okay, so there's our units. I'd have to look, actually. That's a good question. Let me see if they bring it up. Never thought that. Yeah, I don't see, you know what I think they do? I think what they do actually is in some books they'll just use it as, they'll all be just different C's, but I'm using C and then I'm using S for specific heat, so we won't worry about it for now. Okay, so let's do an example here. This is going to be an example of constant pressure calorimetry. So this is where the pressure is held constant. So this is used for reactions. Occurring in solution. where Q equals delta H, and that's what we were talking about yesterday. We were saying that if you keep pressure constant on the system and you only allow pressure volume work, then delta H is equal to the flow of heat. That's what we said yesterday, okay? So this is this is kind of calorimetry is like, imagine you take two solutions and pour them together and they get hot. Or you pour two solutions together and they get cold, okay? So this is the kind of calorimetry we're talking about. We can figure out how much energy is associated with that. So example, and then that's, I think, it for notes, yeah. Example. Let's say a 500 milliliter, 500 ml water sample is warmed from 500 water sample is warmed from 20 degrees C to 100 degrees C. How much heat was required? How much heat was required? Okay. So a couple things I got to give you. 1 ml of H2O is equal to 1 gram of H2O. And the specific heat of H2O is equal to 4.184 joules per gram times degrees C. That number might look familiar because that's how we convert back and forth from calories to joules, 4.184. But it just so happens that a calorie is that value, because we define a calorie based off of water. Okay, so what do I got? Yep.
So what, do we have to fill in the grams with something? Like do you find
No, it's 1 gram and 1 degree. So like when you say,
so that
when
would
you
be
say
the
35 miles per hour,
Okay.
1 hour.
Alright.
Same thing here. So let's say specific heat of H2O, that's one thing we're given. That's 4.184 joules per gram times degrees C. Second thing we have mass is equal to 500 grams. We have a delta T. Delta T equals 100 degrees C, that's my temperature final, minus 20 degrees C, it's my temperature initial, or 80 degrees C. So I can go ahead and solve my equation. So I have this equation that says Q equals SM, or S equals Q over M delta T. S equals Q over M delta T. I want to solve for Q, because they're asking for heat. So I'm going to take my equation, multiply both sides by M delta T. M delta T. And I get Q equals SM delta T. Now to be quite honest, that's the form of the equation that I choose to memorize. Q equals SM delta T. And the reason I memorize that one is because everything's in the numerator. And manipulating it makes it a little easier. You can say S equals Q over M delta T. The reason I give it to you S equals Q over M delta T is that's what specific heat is. Okay, so there's the reason for doing it the different ways. So Q equals, well, specific heat is 4.184 joules per gram times degrees C. M, 500 grams. Delta T, 80 degrees C. And if you look, the grams and the degrees C are going to cancel away, and we're going to come out with Q. And I get 167,360 joules. What I get.
find delta T, you take volume final minus the volume
Well,
or
temperature. Yep, yep. Temperature final minus temperature initial.
Okay.
And so you can solve for any one of those things, okay? Now, these will get a little more complicated as time goes on, so I really suggest you do your homework, not like a lot of guys did last section. Gary's gonna fall asleep. Damn, man. He's out. Gary, man, you're falling apart. You packing again?
Yeah.
Gotcha. Okay. All right, so let's look at some homework here.